we left off last time. If you remember, we're talking about the energy equation. So we finished with momentum, we moved on to energy, and we started off talking about the energy transport equation. And there are lots of equations, right, to go over in the energy case. So maybe we should kind of set in our mind how they relate to each other. So we had the total energy equation. We got that from a balance. Right? We did an energy balance on a box. Started that 2 times ago, just for 10 minutes. Okay, and that gave us something that looked like the first law of thermodynamics. Okay, and we said this has lots of unknowns. How are we going to deal with this? So we tried to get rid of some terms in the total energy equation. So we did that by deriving a mechanical energy equation, which we got from a momentum balance. And that mechanical energy equation had kinetic energy and potential energy in it. And we could use that to subtract out those terms from the total energy equation. We ended up with only an internal energy equation. So that's what I'm saying up here. The total energy balance minus the mechanical energy balance gave us the internal energy balance, which is this guy right here. Okay? And so that's what we wrote up. So that's a change in internal energy of, say, a material element, right? So we can think about this from a Lagrangian perspective, the same as we did with the Navier-Stokes equation, right? Or the Cauchy momentum equation. Okay? So we have a change in internal energy of a material element has to do with these 3 terms, okay? And this was reversible volume expansion that gave us heat. So you could expand or contract and add heat or take heat away. This was an irreversible term that came from shear of fluids. So if I mix something, right, I've got all these velocity gradients, okay, that dissipate and lead to heat. And then this last one was heat transfer back and forth. So if I have temperature gradients, that puts the stuff around. And we said, well, this is great, except I still don't have an equation for temperature. So this is kind of like the situation we were in when we got to the Cauchy momentum equation, and we said we need to get to the Navier-Stokes equation, or the equation of change for velocity. And so equivalently here, we want to get to an equation of change for temperature. And so we did things to the right and left-hand side to manipulate that to get temperatures. So on the left-hand side, we turned this into an enthalpy. H is U plus P over rho. We could do plus PV, but V is obnoxious in fluids because, you know, we like densities. They're things we think about a lot more easily. Okay, and then we used the total derivative for enthalpy to get a C sub P, and then we had the other stuff that we had to deal with. So this gives us a C sub P. This gives us some other stuff, and that kind of goes into some math and rearranges the equation. And then we plugged in the 2 constitutive laws, right? So I said we had to have a balance and constitutive laws to get equations of change. So this is our balance we finally got to. We plug in the constitutive laws, and then we ended up with this. So this is where we got to at the end of last time. And we had just written this up, and we didn't really get to talk about it a whole lot. So I wanted to make sure we paused here and understood what this equation is. So this is an equation of change for temperature. It's the analog of the Navier-Stokes equation. There's just one equation and one unknown. So that's easier to solve than the Navier-Stokes equation. The Navier-Stokes equation, we had 4 equations and 4 unknowns, right? We had pressure and the 3 velocities. We had 3 momentum equations and the continuity equation we had to solve. So now here we just have 1 equation for temperature, 1 unknown, which is temperature, okay? But you can see this is coupled to some other things, all right? So maybe, you know, the 1 equation, 1 unknown is a little bit exaggerated, but, you know, big picture, you can think about that way. Okay, so what are the terms here? So here I have, you know, the same, the rate of change of temperature, okay, times rho C sub P. So it's almost like the enthalpy, but only this sort of part, okay, of the enthalpy. And then over here I have these 4 other terms, and we can remind ourselves what they mean. I said them really quickly last time, but let's make sure we go over them. So the first one here is thermal diffusion, okay? So, or conduction. So if I have temperature, it's gonna wanna spread out, right? So if I have a temperature somewhere, high temperature, low temperature elsewhere, temperature is gonna tend to be even. That's what that term wants to do, okay? These 2 terms, 2 and 3, these are source terms for the temperature. So they're adding heat to the system, okay? And they come from this viscous dissipation term up here, this tau double dot grad V, all right? And so if you remember the tau, Fourier's or Newton's law of viscosity, when we write down that, there were two viscosities. There's our regular normal shear viscosity that we're used to, and then there was a dilatational or a volume viscosity, okay? And that's what leads to these two terms. Mu has the shear terms, and kappa has the volume expansion terms. And so here you can see, that, like you write out this capital phi and capital psi. The capital phi has the grad G double dot grad V parts, okay? And so that has all of the off-diagonal parts of that matrix, all right? And then del dot V is the trace, so it's the sum of the diagonal parts. This is volume expansion squared. This is essentially all the shear components on the other parts squared, okay? And so that's what's going on here, all right? So this looks kind of ugly. It's not really too bad. This is just you take the matrix and multiply itself, basically element-wise. Okay. This one you do the transpose it, multiply by itself element-wise, and then you subtract out 2 times the trace. So that's how that's working out. It looks kind of ugly, but it's not so bad. Your book actually has a different expression. They're equivalent, okay? But it looks a little different. They pull it into a total thing squared. So this one has, del dot V squared. They pull this minus a trace and subtract out the other piece and make that part squared. And you can prove to yourself that it's the same. You go through the vector stuff. Maybe that would be a good example. I don't know. I'll think about that. Okay. So we've got those terms. All right. And then the term 4. Okay. This comes from this P del dot V part, and it comes from this term over here, dHdP and dt. And it's basically all of the reversible stuff when I have changes in density or changes in pressure that affect my temperature. Okay, so I've got this changes in density and constant pressure, and then I have changes in pressure. And so you can think that has to do with my equation of state. So think about an ideal gas or thermo when you do these cycles or whatever, right? Where you compress a gas and maybe its temperature goes up, or you expand a gas and the temperature goes down, okay? All of that stuff is happening in this term here, right? So now we have some region in space, though, where it might be happening, right? So over here, the temperature goes up or down because pressure's changing, and then we have to worry about how that's happening in space and time, okay? So in order to really solve this, we need to know both how the density relates to pressure and temperature. So we need to know thermodynamic equation of state. And we need to know how the heat capacity changes with pressure and temperature. Okay, so basically we need to know all the thermodynamic information. If you know these two things, you know everything about thermo, okay? You know all the phase behavior and whatnot's happening for a single component, all right? And so this equation, to solve it in all its gory detail is nasty, right? This is a mess, and we're never gonna just solve this thing like that, okay? We're gonna simplify it down and find easier cases to solve it, okay? So that's where we got to. So let me pause for a second, and we reviewed like an entire day's worth of intellectual material in 8 minutes. So let's see if this makes sense. What questions, are there any loose threads that are hanging out there that are confusing? Or does this make sense to you? Makes sense. Okay, people online. How many do we have online today? 2. We got the Zach attack or Zach and Dan? Zach and Zach. All right, Zach squared. We've been missing Dan lately. I saw him around yesterday. Has anybody seen him? See any other classes? Yeah, he's in kinetics. All right, he just thinks this one's easy. He can blow through it. All right, I get it. I'm the easy one. You're like, please don't say that. All right. Okay. All right, so that's where we got to. So now I think we're on to 2. To solving and then I'm going to call it the equation of change. Okay. So how do we solve this guy? Well, first thing to do is to talk about some simplifications. So I was trying to think how to divide this up. And I think the easiest way is to think about solids, liquids, and gases. Okay, those three cases end up being quite different and give us something that makes sense. So we're going to start out here with gases. Okay, so gases are in general, they're compressible fluids, okay, that can have a non-zero magnitude for all of these terms. So a gas is like our worst case scenario, okay? In principle, all of those ones can exist. And in particular, compressible flow okay, is the sort of case where we would use all this, okay? So could have non-zero terms. All. Oh no, that's bad English, but I think you get the point, okay? But often, so, you know, if we have a nasty, like, you know, real gas with all this stuff in compressible flow, that's when I could see that hold out, all right? But let's look at it for an ideal gas for a minute. An ideal gas will help us simplify this a little bit. So let's simplify for an ideal gas. Okay, an ideal gas is nice, first because we have an equation of state that we can write down. So an ideal gas we can write down rho is equal to Pm over RT, where P is the pressure, M is the molar mass. So we can put that over here. M is the molar mass. R is the gas constant. Okay, and we have T already. We've had that up there a long time. Okay, and then the other thing is we can write down an expression for the heat capacity for an ideal gas as well. The heat capacity for an ideal gas looks like R over M multiplied by this little guy, F over 2 plus 1, where F is the molecular degrees of freedom. Okay, so for example, for monatomic, it's 3. So if I just have a single, you know, helium, or I guess it's helium, H2, anyway, whatever, argon, I know is the monatomic gas, okay? Or if we have oxygen, diatomic, it's 5. Okay, so on and so forth. So that's nice. We have equations for this that we write down, okay? And so we can take this and evaluate that term at least and simplify our life a little bit. So it turns out if we do d log rho, d log t at constant pressure, this is the same thing as t over rho, d rho dt. Right? You remember the rule about logs and derivatives. So this means I get t over rho. Well, I have to just take the derivative of that guy with respect to t. Well, that's going to give me p m over r times -1 over t squared. Right? And that means I get a negative, t cancels, and I get 1 over rho, and I have Pm over RT. But rho is Pm over RT. So that gives me -1. So that guy simplifies down to a -1. Okay, so the other thing that happens in a gas, if you remember, is that the viscosity is usually really small, right? The viscosity of a gas is really small. And we're going to see in dimensional analysis in a little bit that we can get out dimensionless numbers for these guys. And you know, it turns out the velocity gradient times the viscosity has to be big for that to matter, okay? And so we'll find that these two terms, 2 and 3, really aren't going to matter very much unless our viscosity is big, okay? So we can also drop those two terms. So for an ideal gas then, what we'll get is rho C sub P dt is equal to K rad squared T plus dP dt. Okay, so for an ideal gas, we lose these terms and we have that term left. And so if you look at that problem, when we solve one of these problems, okay, and again, this will usually be for like compressible flow problem, we've got to worry about, you know, this is rho C sub P dt plus V dot grad T, right? That's that kind of, so we still have to worry about the velocity a little bit, right? We still have to know what's going on there, but we only have thermal diffusion and then this weird term that couples the pressure, okay? And so this is still a source term, but it's coupled through the equation of state, and it's really messy. And if you remember doing compressible flow for like the one day we did it in fluid mechanics, it turns out that you have to simultaneously solve the momentum equation and the energy equation and the equation of state all together, okay, to be able to do this, to be able to solve compressible flow. So compressible flow is a hard, all right? So I don't know, that's like my end lesson here is compressible flow is hard. Okay, you have to solve simultaneously. Now, Navier-Stokes equation of change for the temperature and equation of state. Okay, so you have to do like all of thermo and all of fluids together, right, to be able to do that. So that's kind of a fun. Okay, and so a lot of times what you'll see in compressible flow is you'll see tricks. You'll see like radical simplifications of how you can get something. And so like we had this experience with choke flow when we did it in fluids. And you kind of try to rationalize something that kind of makes sense, and then you do this problem, and it's like, okay, and you get this simple equation at the end, but it's really like you have to go many simplifications to get to this, like, you know, simple equation, and it's sort of hard to understand. So there's sort of a big jump between the fundamentals and then getting to the simple equations. So you guys have enough tools to be able to do that. So if like you open your book to compressible flow, you should be able to follow what's going on now. It's hard in fluids because you haven't had thermo yet, right? And so I'm trying to like motivate it with energy equation, these other things. And then, you know, you get to the end and it's like, oh, and by the way, here's this PV to the gamma, and gamma is the ratio of the heat capacities, and you guys are still a little uncomfortable with that and these other things. Anyway, so there's kind of a mess there. But, you know, I'm kind of rambling, I guess, about compressible flow. But from my perspective, it's kind of a, like there are these situations where it's, you know, invaluable. You need to know about this. But the simplifications are really far down the line from some of the stuff we're doing. Like we're talking about how to solve fluid flow equations. As soon as you introduce compressibility, stuff gets a lot harder. And so maybe that's also the lesson too, is that if you're doing something and you're, say, using open foam to simulate something, incompressible flow, and you start to think that compressibility is important, you need to like take a step back and like consider the broader problem at that point, right? Because it's going to get messy really quickly. You can't just like, it's not like saying the viscosity is a little small or a little big, right? It changes the whole problem to say compressibility is important. Maybe that's the sort of lesson. Does that make sense? Okay. So that's gases. Kind of a bummer about gases. number 2, liquids. Okay, so liquids are typically incompressible, right? That's what's great about liquids. So when we say incompressible, okay, we mean that rho is constant. Okay, so there's some important consequences of this thermodynamically. So think about that for a second. When I say something's incompressible, now the equation of state, that's the equation of state. Rho is equal to a constant. It doesn't depend on pressure and temperature anymore. So pressure becomes something weird, it turns out, right? So pressure, now if I change the pressure infinitely, nothing happens to the density. So it's not the same thermodynamic pressure anymore. It's a mechanical pressure. I think I've said this before in class. But so, now I've got to think about some stuff. It turns out that that makes the C sub V, the heat capacity from U, equal to the C sub P, the heat capacity from the enthalpy. Those end up being equal. So it's it messes with thermodynamics to be in this world, okay? But it makes this problem quite a bit easier. So now I get d log rho d log t. That has to be equal to 0 because rho is equal to a constant. And remember that del dot V is equal to 0. That's the continuity equation. So I can't have, this expansion or contraction, right? Because, the density has to be this constant, right? So I can't do that. That means that this term psi V is equal to 0. Because remember, psi was the del dot V squared. Okay, so that guy's 0. So this makes my equation of change look like the following: dt dt is equal to k grad squared t plus mu phi v. Okay, so now in this case, I've got still the convected derivative of the material derivative over here, right? Rate of change that depends on both time and space, thermal diffusion, and now I have viscous dissipation from shear, but nothing from expansion or contraction. Okay, so liquids are yet easier. And finally, the easiest one are solids. Okay, in the case of solids, V is equal to 0. Right? It's a solid. It's not moving around. Okay. They're also, of course, incompressible. Okay. So now we get an even easier expression. Now I have rho C sub P, and then only the partial derivative, T dt, is equal to K grad squared T. Okay, so this is, the equation of change for temperature for liquids. This is the equation of change for temperature for solids. Okay, so the kind of nice thing about this is that we had this kind of big equation that's nasty and has all these 4 terms. And the terms come up in all the different places, or more or less come up in all the places, right? So we have this dP dt term here that comes out in the ideal gas one. This one has the viscosity term, okay? And all of them have the thermal diffusion term, all right? But they get simple in each of these 3 cases, or at least more simple. We only have to deal with one of the terms, all right? So gases, liquids, and solids. So that's A. Questions on this? Oh, okay. Well, I think this one's not too bad. Let's do a little dimensional analysis.
Actually, Dr. Sure.
Please.
What are some, I don't know, not like necessarily numbers, but like order of magnitude, like for the term, the K term and the mu term there? Like, I feel like the K term is usually going to be a lot more relevant.
Are you asking about this versus this?
Yeah.
What you want is like some dimensionless numbers that characterize how strong that term is to that term.
I guess that's exactly what I'm asking.
I think we should do dimensional analysis. That's a great question, Andrew. You want to know, like, when is that going to be important, right? Yeah, okay. So I'm going to punt on liquids for a second. We're going to start with ideal gas. Okay. So I'm going to make this instead of, or I'm going to make it one. Okay. So the ideal gas, we have this guy, rho C sub P, big dTdP is equal to K grad squared T plus D. Okay, so let's think about a physical scenario here, just to help us imagine and do the dimensional analysis. So let's think about our parallel plate example, because it just gives us some easy characteristic dimensions, right? So we're going to have the top move with velocity u. We have a length here. Okay, so we're shearing the system, but we're also going to put a temperature difference across it. So we'll put T1 on top, T0 on the bottom. We'll make T1 greater than T0. So we're simultaneously shearing and we've got a temperature gradient. Okay, we're going to say this is a gas in here, which, you know, rho is equal to what, PM over RT. Okay. And it's got, you know, the gas also has a thermal conductivity K and viscosities mu and kappa. Okay. All right. So if we look at this, remember to do dimensional analysis. What are the steps? Who remembers what the steps are to do dimensional analysis? What do we have to do first?
Right, some dimensionless variables.
We need to get, that's the second step, is to write dimensionless variables. We need some dimensions to make them dimensionless. So we need to identify those dimensions first, right? So think, we have units. The units of the problem are like kilograms or Kelvin. And we need to find enough dimensions in the problem to get rid of all of our units. And so if you remember, there are fundamental dimensions, right? Like all the units kind of depend on each other, except there's some, you know, fundamental number of them, right? So if you have mass, length, and time, you can make all the things in mechanics. Okay, so if we have a mass, length, and a time, we can do fluids. To do energy, we need mass, length, and time, and we need temperature, right? So we need 4 fundamental units to do. So here we can find a length. That one's usually the easiest. It's like the size of the problem in some sense. Here it's the gap height, L. We're going to have a velocity, which will be U. The velocity we're going to use to get our time, right? So that's how we're going to get a time scale. Then we're going to pick a pressure scale, which I'm going to make rho U squared. But this is really the same as fixing our mass scale. I picked a force, or pressure, or a mass. So I could also think of this as a mass, which is rho L cubed. Okay, that's just a rearrangement of, you know, these different scales together. Velocity, like I said, I could do a time, which was, what is it, L over U. Okay, notice that because the density can change, I'm putting a bar over the top of the density. That means the average density. So I want to pick, I don't want to pick a function like this rho is a function. I want to pick a, you know, a constant, right, for my scale. Okay, and then I need a temperature. Okay, for the temperature, I'm going to pick a temperature difference. Because a lot of times in temperature, you don't care about the absolute number of the temperature, right? You care about the difference. So I'm going to call that delta T. I'm going to make that T1 minus T0. Okay, so that's the stuff I'm going to do for the dimensions. Now we get to Andrew's step. Now we need to define all of our variables in the problem in terms of these dimensions, right? So for instance, I'm going to make a time, which is time divided by L over U, right? So every one of the dimensions, I just need to, find the variable where this has dimensions of time, need to divide by the time dimension. If I have x's, right, I have x divided by L. If I have pressures, I'm going to have pressure divided by rho bar U squared. Let's see, density. Density is a variable here in the gas problem. So I want density divided by rho hat, whatever the average density is that I picked out, right? Let's see, what else? Temperature is temperature divided by delta T. Okay, and actually temperature, a lot of times people do the following with temperature. We'll do that here too. We'll make temperature minus T0 divided by delta T. That makes it nice because then temperature will go between 0 and 1 instead of whatever other thing it does. Okay, so that's like the linear, it's not just a pure ratio I have to subtract. Temperatures are kind of weird like that, but that works out pretty easy usually. So we take derivatives and it doesn't matter to have a constant. Okay, so now I take these guys and I plug them back into here, right? So I solve for the pressure, say, in terms of P tilde times rho U squared, and I can plug that back into that equation, right? Because these are just definitions of these guys. So I'm allowed to just solve and plug them back in. It's not, doesn't change anything, right? So let's do that. So if I take, let's see, I'm going to have rho C sub P hat, and then D, and let's see, the temperature should be this guy, so I should get T tilde delta T plus T naught. And then the bottom I have T tilde multiplied by L over U. Okay? And on the right-hand side, I have K. And remember that the grad operator is like L times the, let's see, times the gradient operator, right? So grad squared is going to have an L squared. So this should have a 1 over L squared, grad squared. And then again on T, I have T tilde delta T plus T naught. And then plus, and then I have dP dt. So the pressure scale is rho U squared. And then dP tilde, dt tilde on the bottom, the temperature, or the time is L over U. Okay? So the nice thing about the derivative of the constant T naught, that goes away. Okay, so I just get out the delta T's. So let me rewrite that. Rho C sub P hat delta T divided by L over U dt tilde d little t tilde is equal to K delta T divided by L squared grad squared T plus rho hat U squared over L over U. I kind of already did that one. Okay. So now I pulled out all the dimensions. Now I just need to divide by the term right there, and I can have a dimensionless variable here and a dimensionless variable here. So let's look at what that is. So I'm going to have dt tilde, d little t tilde, and this is going to be L over U rho C sub P hat delta T multiplied by K delta T divided by L squared grad squared T. And on the other side, I'm going to have L over U divided by rho C sub P hat delta T multiplied by rho U squared. Looks like I forgot the R on top of the rho. What's that? Divided by L over U. Okay, so now it's algebra from here, so that L over U cancels like that. The rho hat cancels like that. So this one ends up with a U squared over C sub P delta T. And this one I have one of the L's cancels, the delta T cancels. And come over here and finish it. Annoying, I have to go all the way to the other side. I'll let you write that down. Erasing. Okay, so let's see, I've got dt is equal to, and I can't see all the way over, so I'm going to cheat off my paper. And tell me if I'm wrong. I get the right one there. Just K on the top, right? Just a K. Thermal conductivity K. And on the bottom, rho C sub P LU. Is that right? Rho C sub P LU. That one I get? Yep. Okay. Grad squared T. On the other side, we get U squared over C sub P delta T, right? And this one is P. Okay, so that's what we get. Right, now this number, both of these have names, but they're not as well known as the Reynolds number, not yet, right? So this one is 1 over the Peclet number. And this one is called the Eckhart number. So Peclet number, and this one, Eckhart is, I think, or Eckert, excuse me, Eckert number. Okay, so we can think about what those mean. The meaning of them is actually, well, let me pause there and make sure we're okay on the algebra before I gamble on that. Okay, you comfortable? Yes.
So when you did all those substitutions, why didn't you do that to the first row term as well?
Oh, I did need it. Okay, yeah, that's a good point. I forgot that. So you're right. I should have put a rho hat rho tilt. And then I should have left a rho tilt. Thank you. Thank you for catching that, Brian. It's kind of hard, like I did over there, 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 there. Okay, so what's going on here? So this term, this is a ratio of the convection versus diffusion. Okay, so the Peclet number, it's 1 over the Peclet number. So the Peclet number is convection over diffusion. So this is, diffusion over convection, okay, here. But what that's telling you is, if the Peclet number is high, then my velocities are high. So think I've got lots of shear, and there's not much time for diffusion to happen, okay, relative to the temperature that's getting pulled along. So I've got lots of temperature that's flowing around, right? So as soon as a little bit of, diffusion of temperature happens here, so the whipping that thing along, right? As opposed to when the Peclet number is small, then I've got lots of diffusion, and this thing is just kind of creeping along top. Okay, so that's a Peclet number. Peclet number is one of my favorite dimensionless numbers. I always tell graduate students that you should have a Peclet number of 1 in your research versus like other things you're doing. So that's my nerdy way of saying, like, when you're like, you often have this objective you're trying to get to, right? And if you have a high Peclet number, you're like driving to your objective. It's all you see. Anything that gets in your way, you're just ignoring it. Okay, so some graduate students, that's all they do is they focus on the thing they're doing, then boom, they go after it. Other graduate students are like always meandering around, right? They see something interesting, they go after it. They do this, they do that. They have a graduate student, you know, that's kind of like that. He's always kind of distracted by something, right? So if the problem is if you have a really low Peclet number, right, really high diffusion, then you don't get anything done. The problem is if you have a super high Peclet number as a graduate student, then it turns out that you miss all these opportunities. And research is this thing where you don't always know exactly what you're supposed to do. So you miss all these other things that you could have done, right? And so sometimes if you kind of stop and explore a little bit, you'll find something that's even better than the thing you're doing. And it actually ends up being like your whole master's thesis, your whole PhD thesis, okay? So it's important to kind of like not only have that singular objective. Anyway, so that's one reason I like to Peclet number, because it's this kind of intuitive thing between moving forward and then kind of diffusing around, all right? So maybe that also helps you remember what the Peclet number is. The Eckert number is a ratio between, we can go back and look here. Well, this is inertia, right? This is rho u squared. So this is telling us like inertial stuff. And then we divide it by the stuff over here, which had to do with the enthalpy. So what this is really telling us is like a kinetic energy ratio versus enthalpy. So how much of the fluid was there that we had in the kinetic energy, sort of driving it, versus how much energy was there, sort of enthalpic, enthalpy energy that was possible sort of in the system to be able to move things around. So I don't know, the Eckert number is a little hard for me to conceptualize. I don't know if I did a very good job explaining it, but kinetic energy versus the enthalpy energy. All right, and again, this problem, right, this guy, this term is what happens in compressible flow. So this is what we're trading off. In compressible flow, this piece, we'll see the Peclet number comes up again in liquids. All right, so this one will still be around in liquids. Okay. Trying to think. Oh yeah, this was another way to help us think about this. So think about when we talked in fluids about the Mach number being large, right? Okay, so this isn't a Mach number, but you might remember that we had to have high velocities in order for us to have that pressure density difference that mattered in the trade-off. So I was also thinking about that. So you have to have a high velocity relative to the heat capacity of the fluid, right? So that's the kinetic energy relative to the sort of heat capacity for it to matter whether or not the pressure changes over the fluid. All right, that was another thing I was thinking about, okay? Okay, so that's number one. Number two, let's see if we can finish these. We won't do all of the math out for all of these. Okay, let's think about an incompressible liquid. So again, this one is rho c sub p dt is equal to k grad squared t plus mu, and then this weird phi v term. Okay. So again, we can think about a physical system with U here, a gap of L there, T0 in there, T1 up here, T1 is greater than 0, T0. Okay, now rho is a constant, right? Because it's incompressible. We also have K and mu, and trying to think if there's anything else I missed. I think that's all the things we need, okay? So we can think now, what are the fundamental dimensions? Where they're all the same, okay? All the same things I wrote over there. So the length is L, The velocity is u, which gives us time. The pressure is rho u squared, okay, which gives us a mass as well. And the temperature is delta T, which is T1 minus T0. Okay, so we do all the same stuff to all the variables, except we need to scale this guy, which is our new thing. So this one, phi v, if you remember, it has terms that look like velocity gradients squared. Okay, so to make that dimensionless, we're going to need phi v divided by u over L squared. Because a gradient has a 1 over L, and then there's a velocity, so a velocity per length squared. Okay? So if you take all these and plug them in, all right, what you get out, you get the following. Looks like we'll probably have to end on this one. The t, the little t, is equal to, let's see, k delta t over L squared, divided by rho c sub p hat delta t u over L rad squared t plus mu u squared over L squared rho c sub p hat delta t L phi tilde v. Okay, so that's kind of an intermediate step. That's where I took all these to find the various values, plug them back in, and then I divided by the left-hand side, put it in that term, okay? And what you find, you cancel some terms out, is that this gives you following, which is 1 over the Peclet number, which is just what we had before, rad squared t, plus a new number called the Brinkman number divided by the Peclet number, phi tilde v. Okay, so we had the Peclet number before, so I need to define the Brinkman number. So I'm going to write the Brinkman number up here. Brinkman is mu u squared divided by k delta t. Okay, so the Brinkman number is viscous dissipation divided by conduction. Okay, and so what's going on here is we have the Brinkman number is viscous dissipation by conduction or diffusion. Okay, and the Peclet number is convection divided by conduction. So when we divide them, we get viscous dissipation by convection. All right, and that's what, and it's just a convention of what the Brinkman number is defined as. So that's why we write it as Brinkman divided by Peclet instead of whatever other number was there. That means viscous dissipation divided by convection. Does that make sense? So, so now this is the answer to Andrew's question. I guess we'll just end there, right? So we say, well, when do we care about, you know, what's important, right? He said, you know, it seems like the viscosity might be small or whatever, right? So he's right. If the viscosity is small in a fluid, if I've got something, you know, less viscous than water, and U is quite small, right? Viscous dissipation is going to be really low. But if I have something like a polymer, okay, and I'm trying to put it, you know, shear this guy, trying to do maybe rheology with it, and I'm spinning really fast in a really little gap, right? Then it might matter, okay? And so if my Peclet number is, let's see, that's convection. So I only care about convection because it's going to cancel, right? Yes. So anyway, I have to think about what the, and what's the number here? We have mu u divided by rho c sub p delta t L, right? That's what that's going to end up being. Okay, so that's the combination of variables. And it's often the case, you know, for low viscosity liquids like water, that this term isn't important. okay? But notice the difference between this and solids is that there's still the velocity piece here. So we still get convection that matters. And that's what we'll see is different in solids. Okay, so I think that's all I have. Next time we'll finish up on the last one and do a couple examples and start in on mass transfer. Thanks.
Yeah.